record. Let me share my screen. We're going to try the iPad in landscape mode today. See how this works. Ah, much bigger. Okay, I don't know if that's better or not, but it's at least bigger. Okay, so when we left off on Friday, we were discussing the density of states, which we call omega, which is a function of energy. And we showed how once you calculate the density of states, you can then extract the entropy of your system, which is just Boltzmann's constant times the logarithm of the density of states. Okay, so in other words, essentially one of the primary utilities of the density of states is to allow you to calculate what the entropy is. All right, and so now when we left off on Friday, we were discussing some minor little modifications that we were going to make to how we calculate the density of states in order to make things jive with when we do things with quantum statistics later in the quarter, for one example. All right, so we had that the density of states, we were calculating like so, is 1 over this little fluctuation in the energy that we allowed in order to allow us to calculate a volume in phase space. And then that was times the integral of all the possible momentum and spatial coordinates of our system, such that the energies we were integrating over were between the fixed constant energy of our system and the fixed constant energy of our system, plus this little thing to allow us to calculate volumes. Okay, so now, again, one of the primary reasons you want to calculate this thing is to plug into here in order to get what the entropy is. All right, so in other words, once you calculate this thing, you're probably going to wind up taking a logarithm of it. Okay, so now once we have this, we can calculate the entropy by taking the logarithm of it. And I'm going to neglect writing the limits because you guys already appreciate the limits, okay? All right, so now what we have here is a product of two things. We have an integral over our momentum and spatial coordinates that characterize our system. And we have essentially a meaningless variation in the energy, which we're going to let go to zero eventually anyway. All right, so we have a product of these two things, and you will recall that the logarithm of a product you can always write as the sum of logarithms. So you could write this as KB times the logarithm of the integral of dp dq minus the logarithm of delta E. Okay, now again, this delta E is essentially meaningless. It's just a small variation that we made to the energy that allow us to calculate volumes in phase space, which we eventually take the limit as it goes to zero anyway. And so what you can see here is that what you're doing is you calculate this integral and then you subtract off this meaningless, essentially constant, okay? And then once we have the entropy, the way that we extract information from the entropy is by taking the appropriate derivatives. All right, and so again, what this delta E, log delta E is doing is essentially just setting essentially where the absolute zero of our entropy is. In other words, we don't care. All right, so one of the first things we're going to do is we're just going to stop writing this delta E, because all it does is just shift the overall entropy up and down by some meaningless constant in any case. All right, so that's the first thing we're going to do, is drop the delta E. So no more delta E, because it's just understood that, you know, again, all it's doing is just shifting absolute values of the entropy. Another thing that we're doing is that now if we look at this thing, So again, what this is equal to is the number of states, states per unit volume in phase space, essentially. So in other words, it's essentially just the number of states available to the system. Okay, so in other words, the number of states means that you look at the different possible values of the momentum and spatial coordinates, and you just count how many different values there are. In other words, this thing should be more or less a pure number. It should not have units. But now this thing does have units, right? Because this is momentum and this is position. And so when we calculate this thing is going to come out having units of momentum times units of length to the 3n, assuming we're in 3 dimensions and we have n atoms and or molecules. Okay, now again, this thing should be a pure number, so that's bad. And in particular, if you go and you you change the units that you are working in, which should make a meaningless change to this density of states, it's going to make a non-trivial change of this thing, because again, what it's going to be doing is shifting the values that you get up or down by some conversion factor. All right, so we want to fix this so that we don't ever have to worry about this again. And the way that we're going to do that is just divide by one of the natural fundamental constants that has the appropriate units. That is Planck's constant, because Planck's constant has units of momentum times length. Okay, so in order to make omega meaningless, or not meaningless, it's not meaningless. In order to make it dimensionless, we're going to divide by h to the 3n, essentially just to cancel out the units of our density of states. So what we're going to do from now on is this. All right, and so now again, it's just a constant. And so once we take the logarithm of this thing, what we get is that it's a logarithm of our integral minus the logarithm of Planck's constant, which seems a little crazy. So again, all that constant's doing is just shifting the overall scale up or down by some factor. And now it turns out that by choosing h as the constant that we're using to make this thing dimensionless, first of all, it makes it dimensionless, which is really good. And also when we get into quantum statistics, we'll see that by doing this, what happens is that when we calculate the entropy, that we get that the entropy at 0 temperature is equal to 0, which makes sense. Okay, so again, all this h is doing is setting what the absolute 0 is. And it makes it so that the absolute 0 in entropy also corresponds to the absolute 0 in temperature, which is really nice. All right, and so we're going to be doubly satisfied with ourselves once we see this occur when we talk about quantum statistics. All right, so this is where we're at now. Now, the last modification we're going to make to this thing is what's called the Gibbs factor, which we briefly talked about on Friday, and we will essentially devote an entire lecture to in a few weeks, but not right now. Right now I'm just going to give you a sense of why it's necessary and what it means. But what it boils down to is when you think about the particles that make up your system. Okay, so again, imagine we go back to our box full of atoms and molecules again. And we zoom in on this thing. So let's say we zoom in here. And what we see is one little ball here and one little ball down here. Okay, now, again, currently we are in classical mechanics. We haven't talked anything really about quantum systems yet. So we're still talking entirely about classical pictures of a gas as a bunch of little balls. Okay, so now it turns out that what you can think in the classical idea of a gas, again, you think of the gas as being made up of a bunch of little balls. And in the classical view of things, in principle, you can go and grab one of these little balls and like paint a label on it. So like, for example, I could put a label on this ball that says it's ball number 1. And I could put a label on this one that says it's ball number 2. Okay? So in principle, you can distinguish between the two balls or between any of the atoms in the gas. Okay, but now what we're going to say is that even though in principle you can distinguish between them, it should not make any difference if you essentially just permute the labels. In other words, you can in principle tell the difference between this state, so I'll call this state 1, and this state, which I will call state 2, where state 2 is exactly the same. So the two balls are in exactly the same place. They have, let's say this is P1 and this is P2. So they have exactly the same position and they have exactly the same momentum. Whoops. Come on. So the same positions and the same momenta as they had previously. The only thing that we've done is just switched which ball is which. So now, whereas we had the ball that we painted the big number 1 on up here to begin with, now we're just going to put the ball that has the big number 1 down here. And we're going to put the ball that has the big number 2 on it right here. And so now, what it turns out that when you go through and you calculate the statistics of a gas, and again, we're going to do this in excruciating detail in a few lectures, okay, then it turns out that even though these are in principle different states, these two different states should not contribute individually to the overall statistics of the gas. So in other words, even though these two states are ideologically different, we want to be able to treat them the same. In other words, the permutations of the labels on the balls should not make any difference to the number of states that we calculate, okay? So in classical mechanics, this is what's referred to as insisting that the particles be undistinguished. So the particles should be undistinguished. Okay, so now notice that this is a different word than indistinguishable. Indistinguishable means that you can't even tell them apart in principle. So in classical mechanics, they are in principle distinguishable, but the distinction between them should not make any difference. When we make the transition to quantum statistics, then the particles are really going to be genuinely indistinguishable, that it is genuinely impossible to tell one particle from the other. But in classical mechanics, at least, the particles are undistinguished. So they can be distinguished, they just aren't. Okay, so now what does this do? So in other words, what we have is a bunch of balls which in principle have labels on them telling us which ball is which. Okay, but what we want to do is essentially divide out the number of possible ways that we're able to permute the labels on these balls. So in other words, we want this to be the same thing as, for example, this. So again, same thing. So now all I'm going to do is just permute the first two, like so. Okay, so in other words, these should not contribute individually to our counting of the possible number of states. When we calculate the possible number of states using this integral, they do. Okay, they do contribute individually. So in other words, what we need to do is to calculate how many different ways are there to permute in labels, and then divide our density of states by that permutation factor. And it turns out, as I'm sure you're all aware, the number of ways to permute in labels, whoops, that's not how you spell labels, is equal to n factorial. And it's relatively easy to see that that's the case. Okay, so in other words, what we want to do is to take our density of states, which now we have as this, and we want to divide by n factorial in order to eliminate this overcounting of essentially identical but undistinguished states. Okay, so in other words, we're going to divide by n factorial. Okie dokie? Okie dokie. So this is, in the future, how we are going to calculate the density of states. Does that make sense to everybody? All right, very good. So now, again, like I say, so where this n factorial really comes into, really becomes obvious that it's necessary is when you have, it's what's called the Gibbs paradox. You have two boxes that are filled with identical gases, and then they're separated from one another, and then you unseparate, you allow them to mix. And when you allow them to mix, you would expect, you know, essentially that what you get afterwards is in every way, other than having a division between the two, identical to what you started out with. So in other words, there should not be any change in the entropy. And yet if you calculate the entropy without this 1 over n factorial, you get that the entropy goes up by a crap load, all right? In particular, a factor of n factorial. All right, and so where ultimately the reason for this n factorial is to solve Gibbs paradox, which indicates that the states of a classical mechanical system should be undistinguished. Okay, very good. Very good. All right, so let's go back to exactly where we started today. So where we started today was that we have these two fundamental parameters that we have been calculating, the density of states, which is omega of E, which we are now going to calculate as 1 over n factorial h to the 3n integral dp dq. Integrated over the appropriate limits, of course. From the density of states, you can calculate the entropy. And the entropy, which is also a function of the energy, is just the logarithm of the density of states. All right, so now it turns out that for a large fraction of the remainder of the quarter, we are going to be discussing quite a bit about the entropy. And so what we're going to do today is try to work through an interesting example that sheds some light on what exactly, or another way to think about what the entropy is telling you. All right, so now if you think about this, the density of states, again, what that tells you is essentially all the different possible configurations that your system can be in. So it's a pure number, it's just the number of different ways you can arrange your system. And entropy is just the logarithm of that pure number. All right, so now what we're going to do today is to work through a cool example that illustrates how you can think of the entropy as something related to the amount of information that is being carried by or that is being stored in whatever system it is that you're talking about. All right, and so the example we're going to work through is black holes. So black holes, entropy, and along the way, other than the friends that we make, we'll also learn a little bit about thermodynamics of black holes. All right, so what is a black hole? So a black hole, as the name suggests, is more or less a featureless big black hole. All right, so it doesn't have very many features other than the fact that it's extraordinarily massive. And so now you ask, how massive is it? Okay, so the defining characteristic of a black hole is that its escape velocity is greater than or equal to the speed of light. So the escape velocity, which I will call v sub e, is greater than or equal to c. Well, I guess it shouldn't be equal to, because then that would imply that it could get away. So it's got to be greater than the speed of light. Okay, so where black holes come from, as you are probably aware, are supermassive stars that essentially, when their gas runs out, their fuel runs out, and they're no longer, so the star has two competing forces acting on it. One is gravity is trying to make it collapse, and the other is our good friend thermonuclear fusion. And so thermonuclear fusion, as the gas molecules within the star fuse together, exert an outward pressure. And so the equilibrium size of the star is a balance between the gravitational attraction trying to make it collapse and the outward pressure from the thermonuclear fusion. Okay, so now when a star just about runs out of gas, what happens is that the amount of fusion going on inside the star is no longer sufficient in order to counteract the inward pull of gravity. And if the star is massive enough, the thing just collapses entirely into a black hole. All right, so how big is a black hole? Let's figure it out. So let's do a really simple calculation. Of the size of a black hole. And I'm going to put size in quotation marks, because the mass that's making up the black hole is actually, at least as far as we know, a mathematical point at the center of the black hole. But it turns out that the black hole itself has some finite size that is larger than that. And so that's what we're going to calculate right now. Okay, and so now this calculation is going to be really, really simple and really, really dumb. But now it turns out that it actually gives the right answer. So even if you went through and you did this calculation using, you know, the full arsenal of general relativity and God knows what else, you'd still get the same answer. So we're going to do it the simple way to see what it tells us. All right, so now let's imagine we have a black hole which has some finite radius, r. And we have a particle here at the edge of the black hole that we shoot off at some speed. Okay, so now what we want to do is find the escape velocity of this object. All right, so what we do is we calculate its energy here just as it leaves the surface of the black hole, which we're going to call E0. And the escape velocity is defined such that once the object escapes to infinity, okay, so here at E0, the radius of the particle, so we'll call that R0, is equal to the radius of the black hole. And the final state of the particle is where it has escaped to infinity. And in particular, it escapes to infinity when its final speed is 0. Okay, so now this is a trivially easy energy conservation problem, okay? So now the initial state of our object, we just calculate its total initial energy, which is equal to kinetic, 1/2 mv squared, plus potential. And the potential energy is gravitational potential. And so the potential energy is this, G capital M, where M is the mass of our black hole, lowercase m, where lowercase m is the mass of whatever particle it is that we're talking about, and its initial position is the radius of the black hole. Okay, now the final energy. I should have done that in red in order to remain consistent with my labeling scheme, but what can you do? So the final energy, again, the escape velocity is defined to be such that once it fully escapes to infinity, its final speed is 0, hence it has 0 kinetic energy, and it has a distance of infinity from the object, and hence its potential energy is also 0, which makes it my favorite number. All right, so now what we do is we conserve energy. We just say that the initial energy must be equal to the final energy. So in other words, 1/2 m v escape squared minus g big M little m over r is equal to 0. So easy a biologist could do it, right, folks? And so now what you do is you just solve for R. What is the radius of the black hole? And you can see that the mass of the object doesn't matter. It's just going to cancel out. And you get that the radius of the black hole is 2g big M over c squared. Okay. So what is this? So this is what's called the Schwarzschild radius. Let's see, how do you spell Schwarz? I'm a German, I should know how to spell Schwarzschild. Come on. So this is the Schwarzschild radius. And so in the future, I'm going to put a S on it to indicate that that is the Schwarzschild radius. Now, what does it mean? Again, the actual object that makes up the black hole itself is a mathematical point. In other words, its radius is 0. So what the Schwarzschild radius is the radius away from the black hole where the escape velocity is equal to the speed of light. So in other words, once you go inside the Schwarzschild radius, you can never escape because the speed limit due to special relativity is equal to the speed of light. And hence, once you go into the event, this is what's called the event horizon, the radius of the event horizon. Horrifying movie, by the way. So the event horizon is the outer radius of the black hole. If you go inside the event horizon, you cannot escape because your speed cannot exceed the speed of light due to special relativity, but the escape velocity is greater than the speed of light. Okay, so does that make sense? All right, so this is the Schwarzschild radius. This is the effective size of the black hole. All right, so now let's talk about some thermodynamics of the black hole. All right, now what do I mean by that? What I mean by that is that let's again say we have a black hole. It's got some mass and it has some Schwarzschild radius. Okay, now what's going to happen is some other mass is going to fall into that black hole. What does that do to it? Okay, so mass from special relativity, you know, is equivalent to energy. So by adding mass to a black hole, what you're doing is adding energy to it, right? Because the energy, the mass energy of this thing is equal to mc squared, as you hopefully will know by this point. Okay, so by taking a black hole and adding a mass to it, what you're doing is you're increasing its internal energy. Okay, and so now if you think about a regular object, like your computer or whatever it is, your table, whatever it is you're sitting in front of, if you increase that object's internal energy, what does that correspond to? That corresponds to changing its temperature, right? So what we want to do is think about how, when we add mass to a black hole, how does that affect its temperature? And what does that even mean for a black hole to have temperature? We'll get to that in a moment. Okay, so thermodynamics says that if we add, whoops, let's not use red, that's hard on the eyeballs. If we add energy to a black hole, what we are doing is increasing its internal energy, which you can also call Q. And fundamental thermodynamics says that if I add an amount of internal energy to a system called of amount Q, that what's going to happen is that is going to cause the object to change its temperature by an amount delta T. Now, different objects, when you add energy to them, change their temperature in different ways, depending upon what the object is made out of. And so to take that into account, you multiply this by, I'm going to give it a symbol C/. This is called the specific heat. Okay, so the specific heat is simply a relationship between you add so much energy to a system, its temperature goes up by such and such an amount. And what the specific heat is depends upon what the object is made out of. What's a black hole made out of? All kinds of crap, right? So let's try to find out something about what a black hole is made out of. Let's find what the specific heat of a black hole is. Okay, so by definition, the specific heat, well, let's not say by definition. Let's say we can look at this relationship and see that 1 over the specific heat is related to the change in the object's temperature divided by how much energy you put in. In other words, if we get an expression for the temperature in terms of the energy, we can take a derivative of that, like so, in order to tell us what the specific heat is. Okay, so this is how we are going to calculate the specific heat of a black hole. Now, the next thing we're going to do, so now what is the energy of a black hole? So again, as we talked about up here, the energy of a black hole depends upon how much mass it has. As you add more mass to it, you get more and more energy. So so in other words, the energy of the black hole is just related to its mass. E equals mc squared. So in other words, the differential of E is equal to c squared times the differential of m. Okay, so another thing we can do is, so what we can do is now use this in our calculation of the specific heat. And now you can see why I put the slash on the specific heat, because we've got speeds of light also flying around, and we need to be able to distinguish between these two different c's. So 1 over the specific heat is equal to the 1 over c squared times the derivative of the temperature with respect to mass. Okay, so now all we have to, so in other words, we need what the temperature is as a function of the mass. How are we going to do that? Well, luckily, a very smart fellow who you may have heard of before, named Stephen Hawking, okay, so why is Stephen Hawking famous? Or why was he famous? Well, specifically because he was able to show what this was. So what Stephen Hawking did to become famous was showed what T of M is. Okay, and he did this using a mixture of quantum mechanics and general relativity and all kinds of crazy crap. All right, so that's why he got so famous. So now, what does this mean for a black hole to have temperature? So here was Stephen Hawking's argument. So you guys have taken quantum mechanics before, right? So quantum mechanics says that there is something called the uncertainty principle. And one statement of the uncertainty principle is this, if I'm not mistaken: the mismeasurement in energy times a mismeasurement in time has to be greater than or equal to h bar over 2. In other words, you can only precisely measure either the amount of energy of something or the time at which that energy was produced to some finite degree of accuracy, but you can't measure them both with, infinite precision at the same time. Now, what this means, this allows for something in quantum mechanics called pair production. Okay, and what this means is that you're sitting out in completely empty space, right? So there's nothing in empty space. Okay, so we have empty space. Here it is, a big box of empty space. So now what the uncertainty principle says is that from empty space, you can just spontaneously, out of nothing, produce 2 particles. Okay, so you can have pair production. So you can produce a particle and its antiparticle. So this is the antiparticle, let's say. And this is the particle, let's say. All right, now, clearly it took some amount of energy to do that. So these particles in principle have mass, or they have some amount of energy. So this particle's got some energy E, and our antiparticle is going to have some amount of energy E. And so to produce these two particles, you had to at least supply an amount of energy equal to 2E. But now what can happen is that these particles, so it's a particle and an antiparticle pair, so they can annihilate with one another. And when they annihilate with one another, they give the energy back. Okay, so here we had to gain an amount of energy 2E, and here we lost an amount of energy 2E. And so what quantum mechanics says is that as long as this pair production and annihilation occurs in some finite amount of time, it's perfectly legit. You can do this, okay? So you can produce things out of nothing as long as you give them back before, you know, some finite amount of time. Okay, so now what Stephen Hawking said was, okay, cool. What if we made the pair production occur exactly at the event horizon of a black hole? Okay, so if the pair production is occurring all the time, everywhere around us. And so if you have a black hole, it is also going to be happening at the event horizon. So now what's going to happen sometimes is that one of the particles is going to get sucked into the event horizon while the other is going to escape. And so what you have done is you've, from a pair of what are called virtual particles, because one of the virtual particles gets sucked into the black hole, the other one essentially becomes real and escapes. Okay, that's crazy, right? So now you've produced a particle out of nothing. So you have used up some amount of energy. Where did that energy come from? It has to come from the mass of the black hole. So in other words, you have a black hole with some mass m, and it is constantly radiating particles away from it because of this, what's called Hawking radiation. And because of the Hawking radiation, the mass of the black hole is continuously decreasing. Okay, does that make sense? Pretty cool, right? All right, so now, what Stephen Hawking showed, so he went through all the mathematics of this business. We're not going to do that. I'm just going to tell you what the answer is, okay? So what Stephen Hawking showed was that so the black hole is radiating. That is temperature, right? So the temperature of an object can be characterized by the spectrum of the radiation that it gives off. So the fact that the black hole is radiating particles, that means that it has a temperature. So what is the temperature of a black hole? So the temperature of the black hole, Stephen Hawking showed, I will call that T sub BH, is equal to this, h bar c cubed over 8 pi big G big M KB. Okay, so now notice that a lot of these things in here are constants. So h bar is a constant, which depends upon quantum mechanics. C is a constant, that's classical electrodynamics and special relativity. G is a constant, that's gravitation and general relativity. And KB is Boltzmann's constants, that's statistical mechanics and thermodynamics. So essentially every possible branch of physics is contributing to this expression, which is kind of cool. And of course, 8 pi is also a constant as well. The only variable in this equation is the mass. Okay, so the mass of a black hole depends only on the temperature of a black hole depends only upon its mass in the following way. All right, so now what we have is the temperature as a function of the mass. Let's take this expression and plug it back up in here to get what our specific heat of a black hole is. Okay, so 1 over the specific heat is equal to 1 over c squared times the partial derivative of the temperature with respect to the mass. And when you do this, you get a curious answer. So again, it's something so easy, a biologist can do it. So I'm just going to show you what it is. You can do it at home. Follow along at home, kids. And the expression that you get is this. First of all, the first curious thing about this is that because the temperature is inversely proportional to the mass, you get a minus sign, which is weird. Okay, so you get minus 8 pi kb over h bar c times the mass. And then what we can do is use our original formula up here and replace the mass with the temperature. So we just essentially take that formula and invert it in order to get the mass in terms of the temperature. And when you do that, you will get this, minus h bar c to the 5th over 8 pi g kb times 1 over t squared. So that is the specific heat of a black hole. So as you add mass into it, and as you're adding energy into it, this tells you how the temperature changes. Again, the first curious thing you'll note about this is the minus sign. And what that tells you is that as you add energy or mass to a black hole, it gets colder, which is weird. Okay, so usually most objects, when you add energy to them, they get hotter. A black hole is the opposite. You add energy to it, it gets colder. And you can say some interesting things about that, but we're running low on time. So essentially what this means is that if you have a collection of black holes, it is more stable for them all to coalesce into a single black hole than to have a whole bunch of separate black holes. And so this winds up, so the fact that you have this minus sign here is essentially what contributes to the formation of supermassive black holes, because they all want to bundle together to form one big black hole instead of have a whole bunch of individual black holes. Okay. Okay, so now we know what the specific heat is in terms of the temperature. And it's weird. Now, we also know that, so the next thing we want to do is calculate the entropy of the black hole. If an object has a temperature, it must also have an entropy. Okay, and in particular, as we talked about the last couple lectures, if you know the temperature is related to the entropy by this. Okay? Now, we have an expression for the temperature in terms of the mass, or equivalently in terms of the energy, because E equals mc squared. So what that means is that we can take our expression for the temperature and integrate it in order to determine what the entropy is. Okay, so what we're going to do is we are going to say that the entropy at mass equals 0 is equal to 0. So that's just setting boundary conditions, which makes sense because if there's no mass, there should be nothing there, and that nothing should have no entropy. So that just sets one of the limits on our integral, essentially. Okay, and so if we take this expression and we integrate it, what we will get is this, that the entropy of mass m minus the entropy at mass 0 should be equal to the integral of 1 over the temperature dE from zero energy to the mass energy of the black hole. And again, this is 0. We're going to say that that's 0 just because it makes sense. Okay, so now we just plug in our expression for the temperature. So we get that the entropy is equal to the integral from 0 to mc squared of 8 pi g kb over h bar c to the 5th times mc squared. This, you will recognize, that is the energy. So I'm going to replace this with energy. And then all this stuff is just a mess of constants. So now again, this is a super easy integral to do. And what we get is this. 4 pi kb G mc squared over h bar c to the fifth. And we can clean this up a little bit so that what you get is this. Okay, so essentially what I'm doing there is I'm just canceling out factors of C. So this is the entropy of a black hole. Okay, now we can make this look even cleaner. If we remember, so now we'll remember two things here. So the first thing we remember is that a black hole is going to be a sphere. The surface area of a sphere, so the surface area of a black hole is equal to 4 pi times the square of the Schwarzschild radius. And then you go back to the very beginning of the notes and you remember that we had an expression for the Schwarzschild radius. And so what we can do is absorb some of these constants here in our expression for the energy, in the expression for the entropy into the Schwarzschild radius. The second thing you can remember is that you can take a combination of fundamental constants and combine them in such a way such that the units that it winds up giving you is the units of length. And this special length is what's referred to as the Planck length, which I will call L star. So the Planck length is just a combination of fundamental constants that has units of length. And what that is this, h bar g over c square root. So that is the Planck length. So now what we can do is to take these two things and substitute it into our expression for the entropy of a black hole. And what we get is this. That. Where this A is equal to, was defined to be equal to 4 pi times the Schwarzschild radius divided by the Planck length squared. All right, that is a remarkably clean result, yes? All right, so that's how you calculate the entropy of a black hole. Okay, so now that's the expression. Now, what the hell does it mean? So now think about what a black hole is. Again, a black hole is a big, featureless black hole. Now, typically when you think of what entropy means, entropy is defined in terms of the number of states a system can be in, right? But now a black hole only has one state. It's a big, black, featureless black hole. It doesn't have states, it's just a black hole, okay? So what the hell does this mean? So what you should think of this as meaning is essentially a form of information storage. All right, so what you have here is your black hole. And into the black hole, the mass of the black hole is made up as the accumulation of a bunch of other systems that fall into it. Okay, so call this system 1, system 2, system 3. So you can think of these as boxes of ideal gas, for example. Okay, so now each one of these things has some entropy, which you can measure in the real world. But then once it falls into that black hole, you are never going to see that stuff ever again. Okay? So all of those states that were available to these masses that fall into the black hole, you can think of those states as being information about the available number of arrangements that you can put those systems into. And once they fall into the black hole, you can never see that again. And so what the entropy of the black hole corresponds to is essentially the information, or all the available number of states of the component masses that it's made out of accumulated in one spot. Okay, so in other words, this entropy is something like the information describing component masses. Another way to think of it is that a black hole corresponds to the maximum possible density of information you can possibly have. So maximum possible information density. In other words, if regardless of what a system is made out of, if I think of a system as being made out of a collection of information that describes its possible arrangements, if you take a given amount of information and you cram it in a small enough space, you are going to form a black hole. All right, and so now we're out of time. And so when we come back on Wednesday, what we're going to do is to calculate essentially what is this maximum information storage and how does it compare to, say, the hard drive in your computer. And I'll give you a hint. We got a long way to go before you have to worry about your computer collapsing into a black hole. Okay, but so that's enough for today. We'll come back to this on Wednesday and finish it up. Okay, so I hope that was interesting, cool, and I will see you guys then. Any questions? Do we have any questions? I guess one thing I should ask is that it was telling me periodically that my internet connection sucked. So I hope everyone was actually able to comprehend what I was saying. And if not, I'm going to post the video afterwards and you can watch it all again. Most of the lecture was fine. Okay, good. Glad to hear it. And again, I'm going to, as usual, I'm going to post the video. So if anything was not fine, then you can download it and watch it and hopefully it'll be clear. Okay, so until Wednesday, my good folks. You're welcome, bro.